Good evening, ladies and gentlemen. In tonight's lesson, I'm going to be looking at Newton's laws. Now, Newton's laws is one of those sections that most of you did in grade 11. So for many of you, you actually haven't even done any proper revision on it in matric, because we assume that you knew everything in grade 11. My experience is that grade 11s are not quite as conscientious as grade 12s, and although it's one of those sections that comes back relatively quickly, you do need to make sure that you have gone over it, because it probably isn't as fresh as you think it is if you haven't been practicing. All right, so I'm going to get started and I'm going to go through what Newton's laws are. And then once we've gone through all of Newton's laws, in addition to going through Newton's laws, I'm also going to be doing a bit of discussion of the applications that we do with it, which includes how to work with friction and how to calculate your normal forces. I find that normal forces are a very confusing thing. I'm also hoping that we'll get to do some questions on inclined planes and we'll kind of build up where we're going. So what I usually do with this section is I start with Newton's first and Newton's third law, because those are application questions. You don't have to do calculations on them. Then what we'll do is we'll move on to Newton's laws, which will probably take most of this lesson. And I suspect that I may need to go into Thursday to cover gravitation and the other bits and pieces and just make sure that all of the sections are pulled together nicely. If we manage to do it all this evening, that would be fantastic, but I don't hold up much hope. All right, so first of all, Newton's laws are all laws that were centered around discoveries that Isaac Newton made. Little disclaimer, he may not have been the first person to make them, but he's the person who's currently credited with them. So we're going to look at them. Now, Newton's laws are in an order. So if I talk about Newton's first law, you can't just pick any one you feel like. It's got to be a specific one, and you can't swap one out for the other. If I ask for Newton's first law and you give me the wrong one, it's no marks. Okay, so Newton's first law deals with objects in equilibrium. And it says, an object will remain at rest or continue moving at a constant velocity unless acted upon by a non-zero resultant force. Now, I just quickly need to highlight the very important ideas here. You don't have to use the word object. Some schools use the word body, and that's acceptable. But the ideas that you do need to have is that this will remain at rest, or it will continue at a constant velocity unless acted upon by a resultant force. I know some versions where they do and don't get fussy about the non-zero resultant force. As far as I'm concerned, a resultant force of 0 isn't really a resultant force, but a large number of people put the non-zero in, so it's worth putting in. So Newton's first law basically says that if I take my calculator and I put it down on my desk in front of me, it will remain on my desk in front of me unless a resultant force acts on it. That resultant force could be me picking it up and taking it away somewhere, or it could be that my table breaks and it falls to the floor, but it must have a resultant force acting on it in order to cause it to accelerate and therefore to leave where it is. The second part that many of you seem to forget is that when we're dealing with anything that's moving at a constant velocity, it can have no result. Well, it has to have a zero resultant force acting on it. So anything where we see the words constant velocity, we must know that the net force acting on it is 0 newtons, always. Another way that you've learned to state that is that it is in equilibrium. So if I tell you it's in equilibrium, or it's stationary, or it's moving at a constant velocity, all of these tell you it's in equilibrium and there's no resultant force. One of the branches that we do off Newton's first law is the idea of inertia. And inertia is an object's resistance to a change in its motion. one of the biggest driving forces which determines what an object's inertia is actually its mass. So objects that have greater masses have greater inertia than objects that have smaller masses. All right. Okay, just wait a second. So I've got a question here saying, ma'am, in last year's paper, they made a differentiation between a non-zero and a resultant force equals zero for an object at constant velocity. What is the difference? So they said non-zero resultant force. Okay, so the only thing that I can think of in this particular question, Man, is if the resultant force did or didn't include the weight. But I actually can't tell you the answer to that unless you send me the specific question. So can I please suggest that you send it to me off group on the WhatsApp group just now, and I'll have a look at it and then I'll be able to answer better. All right, I'm not quite certain what the question was. All right, so inertia is an object's resistance to a change in its motion. The most typical example of inertia, there are many of them, but they do that one where you've got the tablecloth beautifully set and somebody whips out the tablecloth and all of the place settings remain where they are. There's also a lot of magic tricks where you perch a coin or you've got a pile of coins and you flick a coin in at the bottom and it just knocks out the bottom coin, but the entire pile of coins stay in one place. I always use the example of bad drivers and my family when I grew up. And we used to do the thing when you're in the car and the car swerves this way and we play crush the brother on this side, and then the car swerves that way and we play crush the brother on the other side. I was always the shortest, so I sat in the middle, but we used to literally crush whichever side was the opposite side. I'm sure many of you have experienced this. So basically the idea behind it is that an object will resist a change in its motion. So if you're in a car, your body is traveling straight. If the car then moves sideways, the bottom half of your body, which is your bum, travels with the car because it's hopefully buckled up. The top half of your body, especially if you're not buckled up, will continue to move straight. But if the car's going this way, straight for you, looks like you're going to the side, which is why you end up crushing somebody on that side. Same thing happens when you are stationary and somebody suddenly pulls off. The bottom half of your body goes forward, the top half of your body remains stationary. But if your bum goes forward and the top half of you remains stationary, it has the effect of you moving backwards. So as soon as somebody screeches off, you all move backwards. And when that same bad driver slams on brakes, your body was traveling forwards at a certain velocity and it continues to. But your bum, which is attached to the car, is tied down and therefore your bum stops and the rest of you goes forward. One of the reasons that we wear a seat belt is to keep our body as if it's attached to a part of the car. There are many injuries caused every year by luggage and objects in the car that aren't physically held down, and then you slam on brakes and you're fine, but something goes into the back of your chair and causes a back injury. We quite often, when we travel with suitcases in the car and they can't go in the boot, but they go in a seat, we actually buckle our suitcases in. Because a suitcase is incredibly heavy, and if it's traveling at, 120 kilometers an hour, when you slam on brakes and it goes into the back of someone's chair, it can cause severe damage. All right. So inertia is the object's resistance to a change in its motion, and you need to know that it's an application of Newton's first law. All right. Can I quickly check at this point? Is everybody okay with Newton's first law? Does anyone have any other questions besides the one question on the difference between resultant force equals zero and a non... Okay, just quickly, if it's a non-zero force, then it isn't zero. I'm trying to go back and try and answer the question, and I'm getting a little bit tongue-tied, but I'm glad that you guys are good with that. I'll take it up just now. Okay, let's carry on. The next law that I'm going to do is I'm actually going to jump one. I'm going to jump to Newton's third law. Now, when I was at school, we had a very bad version of Newton's third law that dealt with the fact that for every action, there is an equal and opposite reaction. You will never get a mark in an exam for that definition. It is so outdated that we don't even teach it anymore. So please, if anybody has taught it to you as being the definition, it's wrong. Lose it. I'm not writing it down. Newton's third law says instead, if body A or object A exerts a force on body B, then body B will exert an equal, that's not equal, an equal but opposite force back on body A. These forces are called action-reaction pairs. And it's very important that you understand that they exert forces on different objects. I remember always asking, one of my favorite questions is, there's a lady, I'll even give her a skirt, pushing a pram. Okay, so there's a baby in a pram and this lady's pushing a pram. And we all hopefully agree that the force of the lady on the pram will equal the force of the pram back on the lady, and that these two forces are balanced. And then I'll go and say to you, if the forces are balanced, surely the force backwards and forwards must be equal. And that means that this lady and this pram can never accelerate. But if you think about it, that's not true. The lady and the pram definitely can accelerate. And when asking people to explain why it is that the lady and the pram can still accelerate, even when the forces are equal and opposite and surely should cancel each other out to give us the situation in Newton's first law, can anyone quickly, who's brave enough, tell me why it is that the lady can still accelerate and that the pram can still accelerate, even though the forces acting on them are balanced and therefore should cancel out? Anyone? Come on, there's got to be someone who's brave. I recommend that when it comes to looking at this question, you realize that these two forces cannot cancel each other out because they're acting on different objects. If I draw a force of the forces acting on the lady, we actually only have the trolley pushing back on the lady. If I look at the force on the trolley, it's only the force forward. So if we look at the lady separate from the trolley, we'll see that these two forces, which are equal, actually act on different objects. Therefore, as long as the lady, okay, so over here, the lady, because there's only a backward force on her, if her legs push with enough of a forward force, she can definitely accelerate. Sorry, that shouldn't have 2 lines, that's not the same. And the trolley, depending on how big the friction is that's acting backwards, can also accelerate or decelerate, depending on the size of the two. So please just remember that you cannot cancel out action-reaction forces because they act on two different objects. They are not going to be something where we can go and say, look, there's a resultant force of 0 because the two forces cancel. Something that's important to note with your action-reaction pairs is that it is always the same two objects. One of their favorite ways to catch you out, and they do this often, is they talk about a person and their weight. And then they ask, what is the action-reaction pair of this person's, or what is the Newton's second law force that is the opposite? So if we consider here with the weight downwards, that is the force of the earth on the man. The action-reaction force cannot be the normal, because the normal is the force of the ground on the man. And then we're muddling earth, man, and ground, and they're 3 things. So you must remember when you do an action-reaction pair to write down what the one force is in terms of this on this, and then the action-reaction pair is going to be the force of the man on the earth. We can also go and say that the man on the ground equals the ground on the man. That's also an option. But if we're talking about weight, the word weight implies earth, and you need to make sure that you consider the earth being part of the system at the bottom. I just realized I've missed an H with earth. Okay, So whenever you're asked for an action-reaction pair that involves weight, it must be the force of whatever that object is back on the earth. All right. So Newton's third law often comes with simple examples. I'm sitting on a chair right now. If my force downwards on the chair was greater than the chair's force upwards on me, I would fall through the chair. If the chair exerted a greater upward force on me than I exerted downward on it, it would fling me up and I'd get flung up into the air. That doesn't happen. If I lean against a wall and I exert a force on the wall must exert an equal but opposite force back on me, or I will fall through the wall. Please note that we quite often use Newton's third laws when it comes to electrostatics and gravitational forces. Okay, and the reason that we consider this is that if you've got a charge and then you've got another charge that's got 3 times as much charge, and these are both positive, you will find that they repel each other, but because of Newton's third law, they both repel each other with exactly the same amount. This exerts a force on this exerts an equal but opposite force back. Similarly, with gravitation, you, tiny little you, exert the same force pulling the earth up as the earth pulls you down. You can all work out right now how big that is. If you have any idea what your own mass is, take it times by 9.8, and that is how many newtons the earth pulls you down with. But it's also the same as the force that you pull the earth up with. So you're actually pretty powerful. The reason that we don't feel like the earth experiences the same force of attraction up towards us as we do down towards it is that our accelerations are different because we have such different masses. All right. So ladies and gentlemen, at this point, we've looked at Newton's first law and Newton's third law. Please promise me that you will go and learn these definitions. All right. I'm hoping that within the next little while, I'll actually manage to get a list of all the definitions you need to know, or all the ones that we know you need to know, and send it through to you so that you can start practicing from them. But the definitions count for a large proportion of your prelims. Most prelims, we've worked out that your definitions alone are about 10% of the paper. That can make the difference between passing and failing, or a 70 and 80%. If you're not learning your definitions, you are throwing away a whole bunch of really easy marks. And the sooner you learn your definitions, the easier it is to keep them in your head. If you leave it till the last minute, you're going to forget them. All right. So I'm going to quickly just stop sharing for a second. Please take a screenshot if you need anything here, because I'm going to clear it as we move on to Newton's second law. All right. So I'm clearing all drawings now. Everybody happy with Newton's first law and Newton's third law? Yes? Okay, fantastic. If you've got any questions, please send them through or just interrupt me as I go. Okay, so we are now going to carry on with Newton's second law. I find that the most efficient way to teach this is to ramp you guys up. I know it sounds really silly and you're going to start at the beginning rolling your eyes and going, no ma'am, I can do that. But I find that if I start with something that's so simple that you can do it, and then build it up incrementally, one new skill at a time, by the time we get to the end, you can do everything and you never actually struggled en route. Whereas if I start with hard things, then I've lost half of you anyway. So please bear with me through the easy things. Newton's second law is the one that you're going to be focusing on. They're likely to ask it, and more importantly, you're guaranteed to need to apply it. So for me, when I get asked what Newton's second law is, this is Newton's second law. F net is equal to ma. But we don't do it from the perspective of F net. We do it from the perspective of A. A is equal to F net over m. What always surprises people is the entire beginning sentence of Newton's law, second law, isn't for marks. There isn't a single mark attached to it. So Newton's second law says, when a resultant force acts on an object, it will cause the object to accelerate. Yes, it could be a non-zero resultant force. I don't really worry about it. Okay, so let me just quickly check. Someone has said something. All right, so there's a question saying, is it silly to ask what happens to an object when acted upon by a zero force? Will it remain at rest or remain moving? If it's already at rest, it will remain at rest. If it's already moving, it will remain moving. If it is at rest, it will not suddenly start moving at a constant velocity. So going back to Newton's third law, if it's at rest, it stays. If it's moving, it stays. It doesn't jump between the two. So it isn't like an option where it can choose A or B. It's either A or it's B, depending on what it started as. Jumping back to Newton's second law. When a resultant force acts on an object, it will cause the object to accelerate. No marks so far, but quite an important line. The marks come in here. The acceleration is directly proportional to the resultant force and inversely proportional, that is spelled right, to the mass of the object. So basically what you need to know is A and F net are both on the top of the divide sign, so therefore they're directly proportional. So you need to know that acceleration, directly proportional, resultant force. First mark. Then second mark is acceleration, inversely proportional, mass. Okay. You also need to have resultant force. So if you don't have this entire first line, then you have to have the word resultant at the bottom. If you've got resultant force at the top, then you don't have to have at the bottom. You may just talk about force. But at least once in your entire definition, you have to say that it's a resultant force. Please be very careful because a lot of you get very muddled up here and you know that something's proportional to something and something's inversely proportional to something else. But I cannot read that the force is directly proportional to the acceleration and the force is inversely proportional to the mass. You get no marks there. So it's got to be very clear that acceleration is the most important thing, and acceleration is directly proportional to the force, and acceleration is inversely proportional to the mass. When we apply this, we're going to be looking quite simply at the idea that F net is equal to MA. Very important and hopefully not too necessary. This is my resultant force, which is measured in newtons. My mass, which must be in kilograms. And this is my acceleration in meters per second squared. All right, so I'm hoping at this point everything that I've said so far makes good and clear sense. If it doesn't, please ask a question immediately. What I'm going to be doing from now is we're going to be applying this equation in a number of different contexts. So we're going to start off with just one force, then two forces, then a force at an angle. When we're doing this, we're also going to be discussing what types of forces we get. So before I move on to them, we need to quickly discuss forces. You're quite often going to be asked to draw a free body diagram. And a very important thing about a free body diagram is that it has to have all of the forces going away from the central object. So if I'm asked to draw a free body diagram, I draw a little circle. To give you an idea, my little circles in most exams, I'd probably say between, 2 and 5 millimeters diameter. On that object, that's the object, we show all of the forces, but they must all move away. This means that if I have a box and I'm pushing it with a force, when I draw it as a free body diagram, it moves away, very importantly. So if I looked at this box right now with me pushing it, and let's pretend it's on a rough surface, if I ask you to draw a free body diagram showing all of the forces, this would be F or F applied, or depending on what they tell you, force of the man. We would have our weight downwards. Please note all objects have got a weight which acts downwards. Then there are two forces that we just quickly need to look at in a little bit more detail. The one force will be friction. Now, the symbol for frictional force, if you look on any memo, is a curly lowercase f, like that. We also differentiate between two kinds of friction. We deal with kinetic friction and we deal with static friction, but on a free body diagram, you normally don't need to differentiate between the two. You can just go and say that it's friction. Please note all of these lines should be beautifully straight. Mine aren't so good. So with friction, you need to know one thing about friction, and that is that friction always opposes motion. Always. I've seen questions where you have an object and a ramp. So imagine here down the side, there's a ramp. And when the object is moving up the ramp, friction will act down the ramp. And then 2 seconds later, the box gets to the top of the ramp and it starts moving down the ramp. As soon as it moves down the ramp, the friction will be up the ramp. Sorry, that should be in another color. The friction will be up the ramp. Okay, now technically this arrow here should be a velocity, and we shouldn't mix velocities and forces, but it's just to give you an idea. So V here just tells the direction in which it's moving. It isn't technically a force. So that is my frictional force. The way that you calculate the frictional force is using the equation F is equal to mu times normal. Be very careful. There are two types of friction. There is kinetic and there is static. So in the one, you're going to say Fk is mu k normal, and if it's static, it's going to be Fs is mu s times by the normal. Please note here, this is friction, which is a force, so it's measured in newtons. This is our coefficient of friction, and the coefficient of friction is determined by the type of materials that we've got. So your coefficient of friction usually for rough surfaces will be high, and for frictionless surfaces is 0. For smooth surfaces, it's relatively close to 0. N is your normal force, which we'll get to in just a moment again. And that's in newtons because it's a force. The coefficient of friction is unitless. It does not have any units because it's a ratio of your frictional force to your normal force. The K stands for kinetic. So whenever we deal with kinetic friction, that is for moving objects. When we deal with stationary objects, we will instead be using an S for static. There we go. Something that you'll notice with your Fs is it usually is Fx max. And that is because when objects are stationary, the frictional force will only be equal to the applied force. So for a particular surface, if I establish that the maximum frictional force, so let's just say we've determined that Fs max is 5 newtons. If I apply 1 Newton, or I pull with 1 Newton this way, then the friction, which goes in the opposite direction, will also only be 1 Newton. The friction isn't going to be all 5 and then cause the object to accelerate. So when you apply an applied force, the frictional force, if it's static friction, will equal your applied force. If I, instead of pulling with 1 Newton, pulled with 2 Newtons, then my frictional force would be 2 newtons. Okay, it's not going to go all the way to 5 and cause the object to accelerate. If I pulled with 5 newtons, it would pull back with 5 newtons, and we call this the point of limiting friction. It's the maximum friction that it can offer, and it's just as the object is about to / starts to move. We often get very technical on that, where we're prepared to say it moves, even though it can't accelerate. If, however, I do an applied force of maybe 7 newtons, the frictional force cannot go above that 5 newtons, and at that point we would start accelerating towards the right. So just be aware of the fact that if objects are stationary, this is a maximum value you can get. It's not the number you're going to get. All right. The last force that I'm going to be quickly discussing with you today is the idea of what is a normal. So over here we've got the normal. The symbol for normal is capital N. I know some people do F, N. It's better to just go with N if you haven't been doing it up till now, and if it isn't going to cause you too much drama to change. And our normal force, I'm just going to quickly write this in somewhere, the normal force is the force of a surface on an object. Please note the key thing about a normal force is that it always acts perpendicular to the surface. A lot of people got this crazy idea at some point in grade 11 that your normal force is always equal to your weight. And that isn't true. Your normal force is equal to your weight if your object is on a flat, horizontal surface and none of the forces acting on it act upwards or downwards at an angle. So for this exact example, it's true that my normal force equals my weight. But it isn't always going to be the case. I can get a normal force right now pushing and holding this pen. That's not equal to my weight. The normal force says that if I push down and squeeze on the pen, if I don't crush the pen or the stylus must be exerting a normal force back on my fingers. Okay? When we have inclined planes, which are slopes, our normal force also isn't equal to our weight. If we've got any component upwards that applies a tension on this box, or if this force, instead of being exactly horizontal, had a slight upwards or downwards component, my normal force does not need to equal my weight. So we're going to be looking at specific examples to see how we can work around it so that you can see what the normal force does, and you can also make sure that you always get it correct. It's important that you get your normal right, because your normal is usually used to determine your friction, and your friction is usually one of the applied forces that later will determine your acceleration. So it's quite a big thing if you mess up on your normal force, because your normal force pretty much knocks on to affect everything else. A lot of these ideas that we're looking at in Newton's second law, if you mess up at one point, it can knock on and make everything else wrong. Fortunately, there are error carry forward marks, which means that you will get positive marking, but quite often not within the same question. It may also result in numbers being very difficult and you actually giving up halfway because the question gets so tricky to look at. All right. Please, can I suggest that you take a screenshot of everything if there's anything that you need right now? All right. And I'm also going to suggest at this point, since we're about halfway through the lesson, that if you need to, you quickly stand up and stretch your legs. All right. So quickly, this is our stretching break. Quickly stand up, stretch your legs, make sure you're not falling asleep on me. All right. Oh, just a quick one. Let's get going. I'm now going to be running through all of the bits as to how you fit them together. So we're going to start really simply, and I know many of you are going to look at it and go, roll eyes, that's so easy. Wonderful. If you think it's easy, that means you've got a good starting point from which to work. So F net is equal to MA, and then frictional force is equal to, and I'm going to deal with here the idea of Fk is equal to mu k times by normal. Please note this letter that I keep saying is mu. Mu. Okay, Greek letters. All right, so we are now going to go and start with a very simple object. We're going to have a 3 kilogram block being pulled with a force of 2 newtons towards the right and no friction. It's a frictionless surface. So if we start here, many of you right now are thrilled. You're wishing you get this in your final exam. F net is MA. Now the first thing that we need to note is, yes, this block does have forces up and down. However, they are not in the direction of our applied force. They are not likely to affect it. Okay, so we are only going to consider the 2 Newton force when we are dealing horizontally. If this object were falling or were tied to a rope and moving up and down vertically, we'd have to start considering it. So here my F net is 2 newtons. My mass is 3 kilograms. We don't usually put the units in there, and we get A. So over here, if I say 2 divided by 3, I get an answer that acceleration is equal to 0.67 meters per second squared. And because acceleration is a vector quantity, I would insist here that you say towards the right. Okay, I know many of you are very excited. Who would be able to do that on their own? Thumbs up. Yay, you guys are brilliant. You're so clever. we're going to bring in one more change. You guys are fantastic. We're going to make sure everybody can do everything the whole way through here. Now we're going to change this question just a little bit. Instead of it just being a 2 Newton force, I'm also going to bring in an 8 Newton force. I'm pretty sure at this point, most of you are still thinking, no, this is cool, this is easy. So let's carry on. So at this point, still no friction. My resultant force has both an 8 and a 2. My advice the whole way through this section is the direction that you pick as positive is the direction in which you think the object will accelerate. So here for my resultant force, I'm going to say 8 minus 2 is equal to 3a. Please substitute in everything, no shortcuts. So 8 minus 2 gives me 6 is equal to 3a, and therefore I get that a is 2 meters per second squared. It's a positive value. My positive meant towards the left, so I can say that my acceleration is 2 meters per second squared towards the left. Once again, nice and easy. At this point, that means that all of you should be able to work out the resultant force, the acceleration, if we have a single resultant force or 2 opposite resultant forces with no friction. We're now going to start making this just a little bit trickier. So the first thing that I want to do is I want to introduce some friction. Okay? So if we introduce some friction here, I can introduce friction by using the words that there is a rough surface and by maybe telling you that the coefficient of kinetic friction was 0,1. So at this point, you can't jump straight to F net is MA because there are 3 forces acting on this object. Because the 8 newtons is bigger than the 2 newtons, friction will move towards the right because it's bigger. We now need to go and work out what our frictional force is. So I'm going to say here, Fk is mu k multiplied by the normal. Now, because this is on a flat surface, my weight downwards is equal to my normal force upwards. So separate calculation again. Fg is equal to mg. The mass is 3. Acceleration due to gravity is 9,8. So if I have 3 times 9.8, I'm going to get an answer of 29,4 newtons. Okay, but I now need to go back here and say, well, actually the normal is also 29,4 because the forces down and up are equal. I like to draw free body diagrams like this. I really find that they help you to be sure of things. So 29,4 newtons downwards, 29,4 newtons upwards. Nothing goes shooting up, nothing goes falling down. But from here, I can say my coefficient of kinetic friction is 0.1. My normal force is 29,4. And if I work those out by multiplying together, I get that the frictional force is 2,94 newtons, which I can now go and put in as part of my diagram. So 2,94 newtons. To work out my resultant force, I need to make sure that the forces towards the left and the right are still not 0. Okay? Otherwise, I may not actually have reached this force. We may not be moving. It may not be kinetic, but I'm happy with what I've done here. So if I say 8, because that's a positive, minus 2, minus 2,9 is equal to my mass, which is 3 times by my acceleration. Sorry, 9,4. So 8 minus 2 minus 2.94 divided by 3, I get that the acceleration is 1,02 meters per second squared, and it's going to be towards the left. All right, so this here introduced one tiny bit more complexity. And that extra complexity that we've got is that we needed to work out what the frictional force was. And then we needed to remember that the friction would act in the opposite direction to motion. And here, the motion, because the 8 newtons is so much bigger than the other force, is likely to be causing us, in this case, if this had started from rest and suddenly started moving, it would be accelerating towards the left. All right, can I quickly double check in with everybody? Everybody still with me? Nothing yet tricky? Hey, fantastic. I know we're going slowly, but we're building quickly now, so please be ready for it. Now what I'm going to do is I'm going to take away the friction again, but we're going to start dealing with what about components at an angle. So what about if I have, let's now make this a 5 kilogram object, and I am applying just one force, and that single force is a 10 Newton force at an angle of 20 degrees. Now the first thing you need to remember to do here is how to resolve your 10 Newton force into its components. So we're going to resolve it into the force horizontal and the force vertical. Those two are at 90 degrees to each other, and I use trig ratios. Many of you will have different ways of expressing your trig ratios. I say sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And I even put in my little lines to remind me. I call this SOHCAHTOA, but I'm very well aware of the fact that lots of people have different ways of doing this. As long as you know what you're doing, I'm not going to interfere. So from the 20 degrees here, the vertical is opposite it, which means that we're going to use sine. We could do, and I'll do the first one slowly, but I'm not going to do any other one slowly. Sine of the angle is opposite, which is FV over hypotenuse, which is 10. Therefore, the vertical component will be 10 sine 20. If I work that out, 10 sine 20, make sure you're on degrees, especially people who do AP maths. I get 3,42 newtons. 3,42 newtons upwards. Okay, if I work out my horizontal component here is going to be adjacent, so I'm going to use my cos ratio. So cos of 20 degrees is equal to FH over 10. So therefore, FH is equal to 10 cos 20. So 10 cos 20 gives me an answer that the horizontal component is 9,396. So I'm going to make it 40 newtons towards the right. Okay. Please note that in this particular case, you can assume that there is a weight down and there is, weight down, let's do only weight down. There is a weight downwards. You don't need to work this out, but I'm showing you what you need to know for harder questions. Our weight down is m times g, which is 5 times 9.8, which is 49 newtons. Fortunately, in this case, since it's a horizontal surface, we are going to have two forces upwards that also equal 49 newtons. The one is my vertical component, and my vertical component here is that value of 3,42 newtons. In addition, there must be a normal force because these two are not yet equal, which means that the normal force must be the balancing so that these two are equal. So you can here say F up equals F down. The force up is the normal plus 3.42 is equal to the 49. You don't have to do this as slowly as I'm doing it, but I'm doing it really slowly because I find that a lot of people mess up on this and they get lost. So over here, the normal force is 45,58 newtons. So in this case, there isn't going to be a vertical acceleration. These two, force up equaling force down, will cancel each other out or be equal to each other, so we don't have to worry. The only force here that's going to cause acceleration is the horizontal component of 9,40 newtons towards the right. So if I now go and work this out, F net equals MA. My resultant force is the 9,40, which is equal to my mass, which is 5 multiplied by my acceleration. So if I work out 9.4 divided by 5, I get that the acceleration is 1,88 meters per second squared towards the right. Now, some of you may wonder why I spent so long showing you how to work out the normal and why I bothered working out the normal. And the reason is that if this story had changed and it wasn't frictionless, we'd have to do this step in order to answer the question. So I'm now going to quickly change the question. Same question, except there's now friction. If there's now friction, and I tell you that the coefficient of friction is 0,1, we're not going to have the same calculation here. I'm going to have to rethink things just a little bit more. None of what I've done up till now actually changes, okay? Okay, sorry, I misread the question and it got me very lost. The question is, what happens if FV is greater than the normal? Then that means that this applied upward force would lift the object right off the table, and we wouldn't actually be dealing with the same question. You'll be dealing with something getting pulled into outer space, which we normally don't do. So for your questions, if the object gets lifted off the table, there will be no friction, first of all, because it's no friction, it's not in contact with the table. And the second thing is that your acceleration will be way more complicated because you'll now have two dimensions that it's accelerating in. It's accelerating right and up, so it'll be getting pulled up at an angle. We usually don't deal with those. We like our objects to stay on the ground. Okay, so if I go back to my friction now, and I've got a coefficient of friction, I'm going to use everything that I've done here. I still need the vertical and horizontal components of the 10 Newton force. I need to know my weight so that I can work out my normal force, and my normal force hasn't changed. But what I will need to do now is work out my frictional force. So Fk would then be mu k multiplied by the normal, which is 0,1 multiplied by 45,58, which is going to be 4,558. I'm going to call it 4,56 newtons. From there, when it comes to my resultant force, I now need to consider that there is a frictional force backwards. So in this free body diagram that I've just quickly kind of put together, it wasn't something that they asked me to do necessarily. I would go and put in that this is 4,56 newtons. I find that everything that goes on a diagram, I see it a bit better, so I always do diagrams for this section. This object would still accelerate towards the right, so I'm going to call towards the right positive. And here we're now going to have 9,40 minus 4,56 is still 5 times A. So 9,40 minus 4,56 divided by 5 gives me an acceleration that is equal to 0,968 meters per second squared. And I've got to put in a direction here, so it would be towards the right. Okay. Can everybody notice, hopefully, that I've taken what was a very simple question, and by putting in a component up at an angle, I've changed what the normal force was, which changes what the friction was, which we then have to include, which makes this question go from being what started off as a really easy one to one that's actually not as straightforward as it looks, and that you actually have to do a little bit of work to do. This question, although it's easy, is kind of the entry level easiest that you can expect in an exam. We can give you a question that's that straightforward. So at this point, I just quickly want to pause what I'm sharing, and I want to ask, oh wait, I don't want to pause sharing, I want to stop sharing, that one. Can I ask who found that going through this slowly meant that they didn't miss anything? Cool. So hopefully, if you'd forgotten anything, I've reminded you now what you need to do to calculate your normal, what you need to do to resolve vectors into their components, as well as how we use the components at an angle. So what I'm going to do now, because I think it's the smart way to check this particular section, is I'm going to ask all of you to try a similar question. This is about as tricky as we can get on a single object. Just now what I'm going to do with you is two objects tied together, moving together, and then you'll see that you can apply what we've just done to even more complicated situations, but you actually can't get more complicated other than if we use an inclined plane, which we can. All right, so let's quickly get going here. Clear everything. I'm going to ask everybody to try this now, but it's the same idea. You've just done it. So this is going to be 8 kilograms. The force here is going to be at an angle of 10 degrees this time. This is going to be a force of 100. No, that's a bit too big. Maybe not. Let's really accelerate it. 100 newtons, and there's a frictional force over here, which has a coefficient of friction, which is 0.2. Okay, so you know that there's friction, you know you've got a vector you need to resolve. My question for you, please, is can you all please calculate the acceleration? All right, I'm going to pause my sharing while I work this out, and then we're going to compare answers. Okay, let's go for this. This is really going to accelerate. Quite a long question. I hope you all are still managing to go forwards. All right, can I check if anybody has an answer? Please feel free to share it. Has anyone finished? Okay, well done. You got an answer, let's share it and let's double check. Okay, good. I like Kayla's answer. Kayla's answer is the same as mine. I hope we haven't both made the same mistake. All right. Just in case you didn't get the right answer, or in case we didn't get the right answer. Ooh, more of you are getting different answers. Very different answers. All right, let's hope we've all got the same thing at the end. I'm going to have to quickly go back and check mine, because one person getting the same answer does not make mine right. Good. Two people getting the same answer might. Unless we've all, as I said, made the same mistake, because it sometimes does happen. Okay. I'm pretty sure mine's right. Okay, ladies and gentlemen, let's just quickly check. All right, lots of different options. So I'm going to share my screen with you, and then hopefully we're going to figure out whether I did any little mistakes. I think we're pretty good. All right, so I'm going to resume sharing over there. Okay, so the first thing that I did was I resolved my 100 newtons into a vertical and a horizontal component. So the vertical component is going to be 100 cos 10. Sorry, that's the horizontal. And then the vertical was going to be 100 sine 10. Then what I did was I worked out the weight to be 78,4. And I said, well, if we've got 17,36 newtons upwards, then the normal would also have to cancel out some of the difference upwards. So it's the normal would be the downward 78,4 minus the 17.36. Remember, the normal is what the surface exerts upwards. If this upward tension here has removed some of the downward force, then the ground doesn't have to exert that force. All right, I always use this idea here of how the normal force becomes less. Normal forces actually are usually what scales measure. So I always imagine or remember back to when I was a young varsity student and I used to travel with overweight bags. So I'd go to the airport knowing that my textbooks in my bag, along with my stuff in my bag, was definitely over the amount of kilograms I was allowed. And I always had this temptation to kind of pick up the bag just a little bit, give it a hand, make the weight less. And that wouldn't actually be a smaller weight. It would just be a smaller normal force because the ground, which the scale acts as when it's working, effectively your scale reading is always the normal, would be less. All right. So from that, I took that normal force using this equation. I multiplied 0.2 by the normal force, got 21.21. I then said, well, my horizontal force is the 98,448 from there. The frictional force is the 12,21. And when I worked that out and divided by the mass, which is A, I got that answer. Please note my answer here would be towards the right. Okay, I'm hoping I didn't pick up anything that I did wrong. All right, so some of you may have made your angles wrong, or I'm sure all of you will have picked up what you did wrong. I'd like to hope that at this point, more of what you did was right than was wrong. Okay, now I'm going to leave this particular skill at this point. There is one thing that I do need to make sure you're fully aware of, and that's that if this force of 100 newtons, instead of acting upwards, had acted downwards. So let's just quickly do a slight version change here. So if I instead told you that the 10 newtons acted downwards, 100 newtons acted downwards at 10 degrees, this would still be right, but this would become down. What this being down makes different is on this question, we wouldn't have 17.36 that way. The 17.36 would go downwards. My normal also now has to compensate for both downward forces. So the normal would actually be plus the vertical component. So if I went and worked that out, 78.4 plus 17.36, this value would change to 95,76 newtons. And this, if we multiply it by 0.2, would change to being 19,152. And can you see we've got a greater frictional force? Anything that pushes down makes friction bigger. Anything that lifts up makes friction smaller because it affects your normal. So here we would have to subtract a bigger value of 19,152. And if we have 98.48 divided by 19, sorry, minus 19,152 divided by 8. That gives me an answer that my acceleration would have changed to 9,916. So just be aware of the fact that you need to realize that your normal gets bigger if there's a tension that pulls downwards, and your normal gets smaller if there's a tension that pulls upwards. What I'd like to do for the remaining 10 minutes in this lesson, we regrettably didn't get as far as I hoped to get because we haven't yet hit inclined planes. So on Thursday, we'll look at inclined planes, and we'll also look at Newton's gravitation. What I'd like to discuss with you now is what happens if we've got two objects that are tied together by a rope. Okay, so this is one of those things that they quite often bring in. And a lot of people get very confused by it. I must be honest, when I was at school, I also got confused by it until a very kind friend took me aside and said, if these two are moving at the same, are moving together, tied together, they will have the same acceleration. It made my life so much easier to suddenly realize that if you've got two objects that are tied together by an inelastic rope, that rope cannot get longer or shorter. The two have to move at exactly the same acceleration. So my advice here for you always is to pick the direction of acceleration of each object individually as being positive. So this will accelerate towards the right, this will accelerate towards the right. I'm actually not going to do this at an angle. If we do it as an angle, you can resolve it into the vertical and horizontal. You can understand that it would affect the normal, it would affect the friction, all of those things. But we're dealing with a very simple example here. So if I have an example, and this is a 10-kilogram truck, train, trailer, whatever, and this is a 5-kilogram trailer, we will have a tension between them. We will have an applied force. I'm going to make this a 50-Newton force. And my question quite simply here can say, please calculate the acceleration. Now, in order to answer a question where objects are tied together, it is so important that you draw the free body diagram acting on each of them. Now, I haven't yet finished this question because I want to make it harder. I also want a frictional force acting on each of them. And I'm not going to make you do coefficient of friction. I know you know how. This frictional force, let's make this 5 newtons. This frictional force, let's make it 10 newtons. In reality, bigger objects, if they've got the same coefficient of friction, bigger objects should have bigger frictions because they'll have bigger normals. So if I look at my free body diagram on the 5-kilogram object, it will have the tension T pulling it forwards, the friction F pulling it backwards. It will have a weight and it will have a normal, but we don't need to worry about those two because in this case, there's nothing that's changing, so we can just assume that they're equal. If we look at the 10-kilogram object, it is going to have 50 newtons pulling it forward. It is going to have 10 newtons of friction. I can even put in what this is as well, pulling it backwards. And it is also going to have the tension pulling it backwards. This tension is obeying Newton's third law. It exerts an equal but opposite force on each of the two objects that it joins. From there, I also need to consider that there's a weight downwards and a normal force upwards, but these two are going to be equal to each other. So the next step that I'm going to do is I'm going to do a simultaneous equation. So for each object, I'm going to say F net is equal to MA. So F net is equal to MA, F net is equal to MA. Choosing the direction of acceleration as positive is the key thing to getting this answer right. Anything that goes in the direction of acceleration is positive. Any forces in the opposite direction are negative. So since my positive is to the right, this tension here is positive T. The friction is in the opposite direction, so it's -5 is equal to my mass here is 5 times by acceleration, and that is equation number 1. Over here, we're going to have 50 minus the T minus the 10 newtons is going to equal 10 times by A, which is equation number 2. So over here, 50 minus 10, I'm going to get 40 minus T is 10A, and I probably should have actually made that bit there once I'd neatened it up just a little bit, equation number 2. Now at this point, the question usually will actually be twofold. question could be calculate acceleration, and then afterwards, usually what they follow it up with is a question that says calculate the tension. So this is a simultaneous equation. We've got two variables and two unknowns. If I'm asked to calculate acceleration, I need to get t out of the formula. So I'm going to show you how I do simultaneous equations. If you do it differently, as long as you get the same answer, there's no issue. So I would say here that t is equal to 5a plus 5 if I get t on its own. Here, if I get t on its own, I take it that way and the 10a that way. So I'm going to get t is equal to 40 minus 10a. So I took t to the right to make it positive. I took the 10a to the left, which made it negative, and then I flipped the sides around because I like the subject to the formula on the left. From there, if this is equal to this, then 5a plus 5 is equal to 40 minus 10a. All constants to one side, all variables to another. So I'm going to move this that way and the a's to that side. So 5a, this 10 goes across and becomes plus 10a. That'll give me 15a is 40 minus 5, which makes it 35. And 35 divided by 15 gives me that the acceleration is 7/3, which is 2,33 meters per second squared. Now, some people have been taught naughty things by, I usually blame the naughty tutors, that you can do all of this super easy by just saying F net is equal to MA for the whole thing. And then you take all of your forces, the 50, the 10, the 5, and you say, well, 50 minus 10 minus 5 gives me 35. We take all of the masses, and it gives us 15 times by A. And look, you end up with exactly what I've got. You do, but you get no marks. So you may not use an approach where you treat the entire system together. You are not going to get the marks. Please do not take that shortcut. It's not going to get you the marks. So it's a lovely check to use at the end. I often quite often go and say that, put it there, add all the masses and work from there. But if that is your step, there are no marks for it. Okay, where the marks usually are allocated, and I can actually tell you for this, 1 mark for the formula, 1 mark for this, 1 mark for this, okay, whatever those are, 1 mark for either one of those. So if you've got 5a or 10a, you get the next mark. From those equations, it's only 1 mark for your answer, okay? So if you struggle with simultaneous equations, you've already got 4 out of the 5 marks just from getting the 2 simultaneous equations without solving. The problem is quite often then you'd lose the mark for the tension in the next step, so you would still want to finish. It's usually not the most difficult maths. But if we then move on to calculate tension, I can take this value of A and sub it in either here or here and get the answer. So tension is equal to 40 minus 10 multiplied by 2,33. So 40 minus 23.3 gives me an answer that my tension is 16,7 newtons. Please note, we do not give a direction for the tension. We can give a direction for the acceleration and say to the right because we know that. But the problem with tension is that the tension is going to pull the 5 kilogram object towards the right and the 10 kilogram object towards the left. So usually when they ask us for tension, they specifically ask for the magnitude, or they ask us what is the tension on the 5 kilogram object. If it's on the 5 kilogram object, I can then say it's 16.7 newtons to the right. If it's on the 10 kilogram object, then it's 16.7 newtons to the left. All right. Ladies and gentlemen, please take a screenshot if there's anything here that you need. Please remember that these are the steps that you're going to do. All right. I'm going to quickly stop sharing, and I just quickly wanted to ask who has found this lesson beneficial in terms of that you've remembered things that you'd forgotten, that you'd overlooked, that are a little bit rusty because they may have been a while ago. The last question that I want to finish off with is where we have 2 objects that are tied together by a string, but one moves up and one moves down. You use exactly the same principle as 2 objects tied together with a string, where one moves horizontally and one moves vertically. The key idea that I need you to get here, without any going around in circles, is if we have two objects joined together like this, the first thing that you need to realize is that their weight becomes important. So if I've got a 5 kilogram object and a 3 kilogram object, I can draw a quick free body diagram for each of them. Here we will have weight downwards and we will have tension upwards. Here we will have tension upwards and we will have its weight downwards. The weight here is going to be m times g, which is 3 times 9,8. And 3 times 9.8 gives me 29,4 newtons. Here, my weight is going to be m times g, which is going to be 5 times by 9.8, which is 49 newtons. And a lot of people mess up here because they don't pick their directions correctly. If you look at these two, the 5 and the 3, it should be obvious to you that the 5 will accelerate downwards and the 3 will accelerate upwards. You need to follow with that. That means that downwards is positive for this side and upwards is positive for that side. So when I use my F net is equal to MA, I'm going to make tension positive and the weight of 29,4 negative. Then I put in the mass of 3 times by A. That is equation number 1. Equation number 2 says F net is MA. Here we are accelerating downwards, so the downward 49 is positive and the tension is upwards, which is negative on this side. You've got to realize that the directions are different for the different sides because they're accelerating in different directions. My mass here is 5 times by A, and that is equation number 2. From here, I'm sure all of you can do simultaneous equations and solve for A and T, but the hard bit is to get those two equations. If we instead did a similar example where we had an object that gets pulled to the edge of a ledge, and the edge of a ledge has a pulley, and this object, so this is a pulley, by the way, I didn't actually mention that. A pulley changes the direction in which a force acts without changing the size of the force. Here, for example, I may have a 2 kilogram object, and over here I have a 6 kilogram object. If there is no friction here, I can work out the acceleration of the system. So I first of all start with all of the forces here. Yes, it's going to have a down and an up, and they're going to equal each other, but we don't actually care what they are unless there's friction. If there's friction, then you've got to work out the normal force and the frictional force and all of that. So here I don't have to. Here, my applied force is the tension. There is no friction. Don't mind about it. Please note this object will accelerate towards the right, so that is the direction that I make positive. The 6 kilogram object would accelerate down, so that is the direction that I make positive. Here on this object, it's going to have its weight downwards. Make sure your free body diagram pieces always touch, and it's going to have tension upwards. The weight is m times g, which is 6 times by 9.8. 6 times 9.8, 6 times 9.8 gives me an answer of 58,8 newtons. So from here, I've got 58,8. Now I can go back and do my two simultaneous equations. F net is equal to MA and F net is equal to MA. Here for this object, the only force is T and it's positive, and that will equal 2 times A, equation number 1. If they'd been frictional forces, you make them negative. Over here on the second one, because it accelerates downwards, it's going to be 58,8 minus T is equal to 6 times A. That's your second equation, and you solve from there. I hope at this point that what you can see from what I've shown you is that if you stick with acceleration as being the direction that's positive and consider all forces acting in that direction as positive and all forces acting in the opposite direction as negative, you don't end up with what I find a lot of students do, where yours looks almost exactly the same as mine, except you've got a different sign there and there. You put t here and minus 49, and you don't know why it's wrong. And sometimes it's right because you guess lucky. Sometimes it's wrong because you guess unlucky. You've got to be consistent. You pick your direction of acceleration as positive and you stick with it, you will never get these questions wrong. They will always follow through. Even if it's choosing acceleration, positive being to the right and down here, and positive being up here and down here. All right, please take a screenshot if there's anything that you need. Okay, I'm going to quickly clear this. And I'm going to stop sharing. All right, ladies and gentlemen, I look forward to seeing you all again on Thursday. Please remember that we're not stopping these lessons just yet. We're still going to do Thursday, and then we're going to do a few more closer to the final exams. All right, have an absolutely lovely evening. I look forward to seeing you all again on Thursday. Bye-bye.